Okie dokie. So I am recording this lecture just in case. So first of all, attendance is I'll be looking at the Zoom report to determine the attendance rather than doing it through Chem 101 today. And that's because there are 3 sections of labs, and so it's easier to do it this way than the way I normally do it. On the right-hand side of your screen, you will see the announcements. Even if UCA is in session tomorrow, I am going to have to postpone the test until Monday. Tomorrow's lecture, I will tell you where the test will be taken at, but I'm having to postpone it because even if UCA is in session tomorrow, there's no way I'm getting out from where I live because of even if the temperatures do get above freezing today, I live in a very shaded area, so the ice is not going to melt for me. So again, I will let you know in lecture tomorrow where the exam will be. This way also, if you do not live on campus and you live out in an area that it's hard to get to campus, it won't impact you either. Tomorrow, because I am postponing the exam, it means I will be lecturing virtually. I will be going over the material I would have gone over on Monday, which is the formation of ionic compounds, and we'll start talking about the formulas and names of ionic compounds. And then I'm also, the study sessions, I always try to make them the night before an exam, so that you've had time to do the homework, the optional homework, and that way you can come with specific questions. So the study session, I'm going to also postpone it from tonight until Sunday from 5:30 to 7 p.m. That way, again, you have time to do the optional homework before coming to the study session. So any questions over my 3 announcements?
Dr. Yarborough?
Yes.
For our attendance, we have to have our cameras on since we all just probably woke up.
No, you don't have to have your cameras on as long as you're participating, because I am going to be asking lots of questions and we're going to be putting our answers in chat today.
Okay.
Because I understand. I really and truly do. Other questions? Okay, so in today's lab lecture, and if a question pops up, I'll try to answer it, but I'm going to go ahead and get started. Today, the way the thing's going to work is I am going to lecture after I get through the topics that will be on this exam. We'll take a 10-minute break because I know it's hard to be on Zoom for so long. And then we'll come back and finish up. So today in the lab lecture, I'm going to start with the size of the cations, which we started yesterday in lecture. We'll then move to electron affinity. Then we'll talk about size of anions and the isoelectronic series. That is where the material for exam number 2 will stop. So I kind of tried to make it 2 different colors. So when you get to names and formulas of ions and all of that, that is going to be on exam number 3. So let's get started into the size of cations. When we ended yesterday's lecture, I had pulled up this and we were starting to analyze this picture to answer some key questions about ions. And specifically, when we're talking about these ions, right now we're going to be looking to the ions on the left. We'll come to the ions on the right later on, but right now we're just looking to the ions on the left. And what you'll notice is they have it listed as the ion and the element. And below that, they have listed the ion's diameter in angstroms and the element's diameter in angstroms. So that just gives you a little bit of an idea of how this table is set up. And this is only going through, it's only going through what would be considered group 1, group 2, and on the periodic tables that I typically give you, group 13. Okay, so what we're going to do is, keeping in mind that particular diagram, this is where we're going to I'm going to try to keep you awake a little bit by having you do some discussion in chat. I want you to try to answer I want you to answer the first question. What do you notice about the size of the cation relative to the neutral atom?
It's smaller.
Right.
Yeah, smaller.
So cations are smaller than their neutral atom. The next thing I want you to do is, what do you notice about the size of a +1 cation compared to a +2 cation compared to a +3 cation? Okay, yes. So what you should notice is that basically, we already said that a neutral atom is larger than a or than the ions, but you can also see that a +1 is bigger than a +2 is bigger than a +3. So basically, the larger the cation charge, the smaller the ion will be. Now, folks, this comes back to Z effective. Remember what Z effective means. Z effective describes how strongly the nucleus pulls on the electron that's on that outside rim. The higher the Z effective, the more strongly that nucleus is going to pull on that electron. And the more strongly the nucleus pulls on that electron, the smaller the species will be. So what I've done is I've given you calcium here. Calcium is the Z effective for calcium is 2.85 for its neutral atom. If you make calcium +1, that Z effective increases to 3.2. If you make calcium 2, that Z effective increases to 8.75. And that was supposed to be calcium 3 plus. The Z effective is 9.1. Now, here's here's an interesting fact. Note the differences. And when we get to the ideal ion, that is when we have this biggest shift in Z effective. That's going to be where it's the strongest. The strongest pull occurs where we have that biggest shift. So let's talk about correlation here. Even though I've kind of already indicated it, I still want you to understand it. So what is the correlation between Z effective and the ion size? The two are inversely related, meaning that as you increase Z effective, the ion size decreases. And here I go. Why does this correlation make sense? Why does that correlation make sense? Sorry about that. Why does it make sense that as the Z effective increases, the ion size decreases? Let's see. The stronger the pull, the closer together the subatomic particles. The atom is losing electrons. Electrons are closer to the nucleus. So yes, basically, Sam's statement is the key. So when we talk about higher Z effective, again, we're talking about the nucleus and its pull on the electrons. So the stronger the pull, or the higher the Z effective, the smaller the ion. Or the smaller the species in general. Girl. Okay. So yesterday we discussed how the breaking of the noble gas configuration and the formation of a cation resulted in the most dramatic increase in the ionization energy. And I drew the electron configuration for sodium. I drew the electron configuration for a couple of them. How did changes in the Z effective correlate with this concept? This comes back to what I was talking about up here. If you think about calcium, this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Calcium plus would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Calcium 2 plus would be 1s2, 2s2, 2p6, girls, 3s2, 3p6, and calcium 3 plus would be 1s2, 2s2, 2p6, 3s2, 3p5, with this being the exact same as a noble gas. So the question is, how does Z effective and the electron configuration that we discussed about the other day, how do those two things correlate?
Well, I have a question.
Yes.
Okay, so you were saying that the difference where we get this is this 5.55?
Yes.
That's the ideal ion. Does that have anything to do with it? Because once you reach, the same electron configuration as a noble gas, then it's harder to, take away and add electrons.
Yes, that is what I was trying to get at, is basically at the ideal noble gas, if you try to take away another electron, it's going to be challenging. So you don't want to break a noble gas, because a noble gas, once you get to that noble gas configuration, that's when you're going to jump to the best Z effective with that, as far as, and that's why the difference is so large. Enough, girls. That's why the difference is so large. Girls. So down to this question, yes. When you reach the noble gas configuration, you will notice the highest, or the greatest difference in the Z effective. That is because once you reach a noble gas configuration, a lot of energy must be added to break a such a stable configuration. So again, when you reach that noble gas configuration, what you've got when you've got the noble gas configuration is an extremely stable configuration. And because it's an extremely stable configuration, that's where the Z effective all of a sudden will pop up, because now you have hit that extremely stable configuration. Anything that causes you to break that stable configuration is going to cost a lot of energy. Any questions about that? So basically what I'm trying to get at is Z effective, ion size, and ionization energy are all interrelated. They're not completely different concepts. They're all related. Because Z effective ionization energy is talking about the energy needed to remove an electron. I mean, it's talking, well, ionization energy is talking about the energy needed to remove an electron. The higher the Z effective, the closer those electrons are held to the nucleus, therefore more energy is going to be needed to remove an electron. And the higher the Z effective, the smaller the ion will be. So ionization energy, again, is the energy associated with formation of cation. Electron affinity is the energy associated with the formation of an anion. And just like with ionization energies, when we start talking about the formation of an anion, we add the electrons in step by step. So we add one electron at a time. The first electron added would be the first electron affinity. The second electron added would be the second electron affinity, and so on and so forth. Now here is a table of electron affinities. Now, what you see at the top is the old group naming method. Now we use, this would be group 1, group 2, but this would be group 13, 14, 15, 16, 17, and 18. I want you to take a moment and I want you to look at this, and then we're going to talk about its meaning. And I mean, things to notice is where do we find the highest negative value? Note nitrogen and beryllium and neon, stuff of that nature. So I want you to take a moment and just look at this table and kind of digest it. Okay. So first thing I wanted to do is make a couple of notes. I indicated this yesterday, but I did, or a couple of times, but I haven't explicitly stated it. So I want to talk about the signs on our numerical values. When you think about mathematics, you think about plus being that you have a gain of things, and you think about negative meaning you have a loss of things. But here's the deal. Can you ever truly go below zero? Can you lose more than what you had to start with? No. When we talk about signs in chemistry, the signs indicate whether energy must be absorbed by our system or our element in this case to make something happen, or whether energy is generated as a result of something happening. When you see a positive number related to energy, it means that that species had to absorb energy for the process to occur. When you see a positive energy value, it really means that it is not a favorable process all on its own. We're not saying that it's not going to occur. What we're saying is that it's not going to occur on its own. It cannot occur on its own. You have to add energy to make it happen. An example was the sodium ion. When we take and look at the first ionization energy of sodium, that is the energy needed to take a sodium atom and rip off an electron to make a sodium ion. In the ionization energy table that I gave you, it required 496 kilojoules of energy to rip off an electron from the sodium atom, meaning we had to add 496 kilojoules of energy to get that electron to be removed from the sodium atmosphere. And we have to add that energy because we had to overcome the Z effective. Again, formations of cations is not favorable on their own. It's just not going to happen all on their own. Now, when you see a negative energy, a negative energy means that when the process occurs, energy is released by the system, in this case, an atom. Because energy is released by the system, that means that this is going to be a favorable process. An example will be the formation of the chloride ion from chlorine. When you take chlorine and you add an electron to chlorine, the chlorine becomes chloride, which is the Cl- ion. And it gives off 349 kilojoules of energy when that chlorine gets to accept that electron. So I just wanted to take a moment to go through this concept of what the positive and what the negative means when we're talking about energy. And now we're going to go back and look at that table a little bit more with this new nugget of information. And I'm trying to make sure I give you plenty of time to keep up with me in writing. So let's go back and look at this table and take another moment to evaluate this table based on this new nugget of information. In answer to Jasmine's question, yes, I plan to post this one because it is such a long lecture. It will probably be next week before it gets posted though, because of internet issues. Okay. So what do you notice, or what did you notice about the electron affinity for atoms that traditionally form anions? Those are your nonmetals and metalloids compared to those that traditionally form cations, which are your metals. I'll go back. So let's look at the question one more time, and then I'll go back to the picture. What do you notice about the electron affinity for atoms that traditionally form anions, those being your nonmetals and metalloids, compared to those that traditionally form cations? What do you notice about the elements that traditionally form anions, those being your nonmetals and metalloids, compared to those that traditionally form cations, which are your metals? Yes. Fluorine, chlorine, bromine, iodine, oxygen, sulfur, selenium, tellurium, those elements, and even we'll talk about group 15 here in a minute, but those elements tend to have a larger electron affinity, meaning that they give off more energy as the result of forming the cation. I mean, the anion, excuse me. So what we can say is a greater amount of energy is released by elements that traditionally form anions compared to those that traditionally form cations. And again, the greater amount of energy that's released, the better it is. Now, you will if you go back, let's go back now and look at that table. And I said, pay attention earlier to beryllium, nitrogen, and neon. And basically, you'll notice that group 2A or group 2, group 5A or group 15, and group 8A or group 18 behave a little differently than the other elements in the series. So why or what could we use to explain why their electron affinity doesn't behave as expected? What could be the reason their electron affinity doesn't behave as expected? Exactly. Beryllium has a full subshell. Nitrogen has a half-filled subshell. And your noble gases have a full subshell. Full subshells and half-filled subshells are particularly stable. So anything you do to interrupt that stability can cause issues. Now, obviously nitrogen does form an anion, phosphorus does form an anion, but they do so reluctantly, or at least more reluctantly than their counterparts of oxygen and sulfur, or fluorine and chlorine. So keep in mind, I told you everything we've been talking about is all based on their electron configuration. The Z effective is all based on their electron configuration. The ionization energies was based on electron configuration. The now electron affinity is based on electron configuration. So the electron configuration really does help us understand why elements behave the way that they do. So now we've talked about electron affinity. Again, electron affinity is simply the energy associated with the formation of an anion. And yes, the elements that traditionally form anions, which are your nonmetals and metalloids, those elements have a greater electron affinity than do the elements that have that traditionally form cations, which are your metals. Now let's talk about the effect that the formation of an anion has. So we're going back to this diagram again. Now we're going to look to the, whoopsies. Now we want to look to the right. Of that line. Again, this is group 16 and 17. You will note the element in its standard state is in gray, and the ion is in blue. The size in angstroms is listed below. I want you to take a moment and look at these elements. Look at the same period of elements. Look down a group of elements. And they're traditional anions. Because we're going to answer some questions based off of your observations. So, what did we notice about the size of a neutral atom compared to the size of an anion? Anions are bigger. Okay, now, because I couldn't remember if I asked this question specifically, what do you notice about the size of the anion relative to the charge? What do you notice about the size of the anion relative to the charge? Okay, yes, the more negative the charge, the larger the ion. Now, let's talk about Z effective. Here is the Z effective for nitrogen. Nitrogen as a -1 charge, nitrogen as a -2 charge, nitrogen as a -3 charge. And I want you to answer the question, how does the size of the anion correlate to the Z effective? Okay, so yes, we just said, it'll let me do this. The more negative the charge, the larger the anion. This is because the Z effective decreases. With the addition of electrons. Folks, it makes sense to me when you start thinking about it. I'm going to do it just with something super simple because it's harder for me to get too complicated. So let's just talk hydrogen. Hydrogen, you have your +1 and you have your electron here. Originally, you have just this, the Z effective is the attraction of that proton to that one electron. In other words, that proton gets to spend all of its attention on one electron. It gets to focus all of its time on one electron. But when you add a second electron, now that single proton splits its time. And it's kind of like a parent. In fact, I love to use this analogy when I'm talking about size of ions. It's kind of like a parent. You know, you got one kid, well, you get to spend all of your time with that kid. You're doing all their activities with them, stuff like that. But if you add a second kid, a good parent is going to make sure that they give each kid equal amount of time. The same, and because of that, the kids have a little bit more freedom to run around and do what they want because the parents not keeping up with them. So it's the same concept here. Because that proton is going to wind up, originally has only the one kid, the one electron, and it spends all of its time working with that one electron. But once you have that second electron added, now it has to split its time. Thereby, this one electron that it originally had is going to have a little bit more freedom. And so the size of the ion grows. Okay. So the last thing we're going to talk about is an isoelectronic series. Before we take our break, I should say. The last thing we'll talk about is an isoelectronic series. The term isoelectronic. Iso means the same. Electronic means the same number of electrons or the same electron configuration. So that's what the term isoelectronic means. Is iso means the same. Electronic, electrons, same electrons, same electron configuration. So Na plus, neon, and fluoride, F minus, are all isoelectronic species because all of them have 10 valence electrons. I mean, not valence. They all have 10 electrons. And they all have the exact same electron configuration, which is 1s2, 2s2, 2p6. So today we discussed the fact that cation size decreases with increasing charge. So that it means that a +3 is smaller than a +2. A +2 is smaller than a +1. A +1 would be smaller than the neutral atom. We also have discussed that the anion size increases with increasing charge, meaning that a -1 is smaller than a -2. A -2 is smaller than a -3. And we've discussed how Z effective is related to this concept of ion size. Now, what we've got to do is we're going to see, does this concept of the impact of Z effective fit with an isoelectronic series as well? Do these statements we made about cations being smaller than neutral atoms and anions being bigger than neutral atoms, does it fit with an isoelectronic series? So I went ahead and calculated the Z effective for an isoelectronic series. We know this is isoelectronic because if you look at the electron configuration for all of these, it would be argon. I gotta make sure, well, it'd be 4. Argon 4s2, 3d10, 4p6. They all have that particular electron configuration. They all have a total of 36 electrons. We have said that the larger the Z effective, the smaller the size. That's what it boils down to. So with these elements here, if this is the case, then Y3 plus is smaller than SR2 plus, is smaller than KR, is smaller than BR minus, is smaller than arsenic. And folks, this is a fact. So yes, the same concepts we discussed for cations compared to their neutral atoms or anions compared to their neutral atoms fit for an isoelectronic series as well. Questions about this part of today? This is where the information for exam 2 ends. So what I want to do is we're going to actually take a 14-minute break, come back at 9:10, and we are going to pick up with the information that is related to exam number 3. Now, you will want to be here because what I'm going to be discussing is ions. We're going to talk about how to name the ions. We're going to talk about how to determine the charges. And we're going to talk about this concept for both monoatomic ions, which are ions of elements, as well as polyatomic ions. Now I'm going to give you a list. Now, I will say in your Blackboard folder for this week, there was a folder that had extra materials. What I'm about to discuss will be referring to those extra materials that are in this week's Blackboard folder. So if you have a printer, you may want to print it out in the next 14 minutes. Well, now it's 13, but you may want to print it out so that you can follow along a little easier. If not, you can print it out at any time. But I will be referring to those documents. Okay, so let's take a break. I am just going to mute myself. So if you have questions, you can always put them in the chat and I'll try to answer. See you back at 9:10. Okay, folks, I show that it is that time, so I'm gonna go ahead and get back into the information for today. And again, what I am about to discuss is going to be the information that will be on your next exam, not the exam on Monday now. So it will be on exam 3, which will be, so just to keep that in mind. So what I'm going to do today is I'm going to be discussing ions. And there are 2 types of ions that we will be discussing. There will be monoatomic ions. These are going to be the ions of the elements. And there are going to be polyatomic ions. And these are going to be ions that consist of more than one atom. There is a large number of ions that you need to be prepared to work with. And so one of my goals for today's lecture is to help you figure out how to learn those ions, because there are trends within the ions that will greatly help you in remembering the ions. And now I will say this, while what I'm going to describe works for a lot of ions, there are some ions you just are going to have to memorize. But I'm trying to get you a method to memorize as many as possible so that it's a little bit easier. When we talk about the monoatomic ions, again, these are going to be ions of the elements. The metals will form cations because they have the lowest ionization energy. And the nonmetals and metalloids will form anions because they have the greatest electron affinity. One of the documents was 2 pages worth of ions, and it listed some of the monoatomic ions. It doesn't actually even list all of the monoatomic ions, folks. It lists some of the monoatomic ions. And I tried to do some color coding in this list to help you pick up on one fact. The cations in blue, which are in the top left part of the table, and the anions in blue, which is in the bottom right-hand side of the table. These elements, when they are part of an ionic compound, will always form the exact same charge. What that means is silver, for instance, no matter what ionic compound you find silver in, it will be a +1 charge. Chlorine, for instance, no matter what compound you find chlorine in, it will be a -1 charge as long as it's an ionic compound. So again, the metal cations in blue and the non-metal metalloid anions in blue, those will always have the exact same charge. Now, all other metal ions, you will note the majority of them can have more than one charge. For instance, chromium can have 3 different charges. It can be chromium 2 ion, it can be a chromium 3 ion, and it could be a chromium 6 ion. Where the number that I just described is the charge of the cation. With respect to all of the metal cations in black, you will not be asked to memorize them, but I'm going to show you once we get to the formula of ionic compounds, I will be showing you a method to determine what the charge is. So again, I'm not asking you to memorize all the ones in black, because once we get to the formulas of ionic compounds, I will be demonstrating how to take the formula of the ionic compound and determine what the charge on that metal is. Now, before I move off of this page, I do want to make a couple of other notes. The first thing is I want you to look at the metal cations in blue and the metal cations in black, and tell me what difference you see from this table. What is something you notice? Let me get my chat back up. I want you to look at the metal cations in blue and the metal cations in black and tell me one thing you notice.
None of the metal ones have Roman numerals.
None of which metal ones?
So like none of the like potassium, rubidium, cesium, francium, beryllium, or nitride. But like the scandium, titanium, they have like different Roman numerals to identify which ion is which.
Okay, that is the key. Yes. So you'll notice that the metal cations in blue, which are the ones that I said always have the same charge. I just gave you the name of the element followed by the word ion. And that is sufficient because again, those metals, if they're a cation, they have the exact same charge. It doesn't matter what compound they're in, they have that charge. But for all of the metals in black, those were the ones that can have different charges. And so we have to indicate what charge they possess. We have to state whether it is chromium 2+, chromium 3+, or chromium 6+. And we do so using a Roman numeral in parentheses. That Roman numeral is equivalent to the charge that that element possesses. Now, I did highlight 4 sets of elements in yellow. These 4 elements are 4 of the elements known to the ancients, along with gold, which I did not put on here, but these are 4 of the elements known to the ancients. And as an element known to the ancients, they have a name that was given to them by the ancients. For instance, lead is called plumbum, Plumbum. That's why its symbol is Pb, is because according to the ancients, it was plumbum. Mercury, well, it's always been known as mercury. Iron used to be known as ferrum. Now, the reason these are highlighted is because since they were known to the ancients, their ions were also known to the ancients. And we have an old methodology for naming these ions. The cation with the lower charge gets the letters OUS at the end, whereas the cation with the greater charge gets the letters ic at the end. So iron 2 is ferrous, whereas iron 3 is ferric. Now on a test, if you decide to name it that way, that's fine. But the main reason I've highlighted these is because when you get into Chem 101, they sometimes use the old form of the name. So I wanted you to have it available just in case. Now, before I move off of this page, I also want to talk about the anions of the elements, which are on the far right-hand side in blue. And something was, I mean, it was already made note, but what do every single one of those anions end in?
Ide or
They all end in "ide." So basically, your halogens, chlorine, fluorine, bromine, when they take on that negative charge, they become fluoride, bromide, and chloride. So as soon as an element becomes an anion, the ending changes to IDE. This is actually very useful as we progress to the polyatomic ions, because elements end in IDE, whereas polyatomic ions, for the most part, end in ATE or ITE. So there is a difference in the ending that will help you to identify whether it is an anion of an element or an anion that is a polyatomic anion. And we'll get more into that as we progress. But I wanted to just take a moment and us look at that. Oops, spent too long on that one, I guess. Now, the other page, on that page, you'll see in the middle on the right are two cations that are polyatomic cations. They are ammonium and hydronium. Those are important. But the majority of polyatomic ions are in the form of anions. So the majority of polyatomic ions are anions. Other than ammonium, well, there's three: ammonium, hydronium, and mercury 2. I mean, mercury 1. So again, if you look at these tables, that's a lot of ions to know. If you simply try to memorize them, you're going to get overwhelmed. I'll promise you, my memory is not that good. So I have ways to help you learn them. Because yes, you're going to need to know all of these ions. My goal today is to provide you some tools to help you memorize some of these ions. Again, I can't help you memorize all of them, but I can help you memorize some of them because there are trends in the ions that will help you to memorize them. So we're going to start with the monoatomic cations. Again, there were two types. The metals that always form the same charge, to name them, we said you'd give the name of the element. Followed by the word ion. Basically, we have to tack the word ion on to distinguish the ion from the element. So we tack the word ion on simply to distinguish the ion from the element. The second type of monoatomic cation was the metals that can form cations of various charges. And in that case, we named the metal, followed by a Roman numeral, equal to the charge, followed by ion. And just for those that need it, I is 1, I is 2, I 3, IV 4, V 5, VI 6, and VII is 7. And we don't have any that can go above 7. Now, to help you remember who's who among this grouping, who's who, we're going to look at the periodic table. And I actually drew this previously on a blank periodic table, but now I've actually included the names. So Li plus is simply lithium ion, or Be2 plus is simply beryllium ion. You will notice that group 1 metals form a Group 1 metals form a +1 charge. Group 2 metals form a +2 charge. That's true for all of them. Over here, I drew my stair step that I showed you the other day. One step has +1. The 2 step, the one that has 2 elements in it, they're both +2. And then you have the 3, which are all +3. All other metals have multiple charges. So those you're going to have to determine. So again, helping you memorize. Group 1's always +1. Group 2 is always a +2. Because they always have the same charge, you name the element followed by ion. Starting with silver, you can draw a stair step. The number of elements in the stair step is equivalent to the charges. Again, because those elements always have that same charge, you name the element, followed by the word ion. All other metals, the only way to determine what charge they have is to look at the ionic compound that they are part of. And I will be showing you, once we get into formulas and names of ionic compounds, how to determine which charge the metals have. Now, the other thing I wanted to show you is you'll notice group 15. Your group 15 always formed a -3. Your group 16 formed a -2, and your group 17 nonmetals formed a -1. They always will have that charge as an anion. And to indicate that it is an anion instead of a neutral atom, to indicate that it is an anion, we use the ending IDE. That tells us we're dealing with an anion of that element. Any questions? Again, this table is one of the things you can print off. So again, the anions of the elements, if they have a -3 charge, we change the ending to IDE. If they are in group 16 and have a -2 charge, we change the ending to IDE. And if they're in group 17 and have a -1 charge, we change the ending to IDE. So what we can say is, for the most part, if an ionic compound or if you have an anion, ending in IDE, it is an anion of an element. Your polyatomic ions. Poly means many, atomic atom, ions means that it's charged. Now, with respect to these polyatomic ions, the element ratio, along with the name of the polyatomic ion, along with the charge on the polyatomic ion, are always constant. They are always the same. I told you one of my goals is to help you memorize the ions And this is where we're going to start working on that aspect even further. Is because when I pull up the next diagram, I want you to note the charge of the monoatomic ions and the charge of the polyatomic ions starting in period 3. I'm also going to show you some other things, though, that are extremely important as well. Again, the next diagram I'm about to show you is something you can find in that folder that you could print off to help you see the connections, which is one of my goals, is for you to see some of the connections. So let's get into this diagram. Okay. So what I want you to do is let's just look at phosphorus for a moment. And sulfur for a moment. What do you notice about the charges?
They're all the same. Like for phosphate, and phosphide is all -3.
Exactly. So in other words, so let me ask this question. If I know phosphide, which is the anion of the element, if I know its charge, do I really need to memorize the charge on phosphate or phosphite?
You do.
Or is it the same? You don't have, in other words, you don't have to memorize the charge for phosphate or phosphite if you already know the charge for phosphide. Because they're all the same. The same thing is true for sulfate and sulfite. If I know the charge on sulfide, the anion of the element, then I know the charge of their polyatomic ions as well. So I don't have to memorize the charge on the polyatomic ion. I know that it is the same. Now, this is only valid, that statement though, is only valid if we are talking about period 3 and down. So what I just said only works for period 3 and down. But hey, that's 8 elements worth of ions. And not just a few ions at that. I mean, we're talking about, by knowing that one concept, I know the charge on 22 ions that are polyatomic ions. I didn't have to memorize those polyatomic ions, at least not their charge. Unfortunately, I can't say that that is the case for period 2. So that's why I said it only starts at period 3 and down, because unfortunately it doesn't work for period 2. It's okay, Luna Bear. But it does work for all the elements period 3 and down. Any questions about that? Now, the next thing I want you to note, and I've tried to highlight the letters here. For period 2, I want you to look at the 8s. For period 2, look at the 8s, ATE. How many oxygens does the ATEs have?
Three.
4.
For period 2, they all have 3. For period 3 down, they all have 4. So in other words, if I see the word ATE, I go, okay, is it in period 2 or period 3 down? If it's in period 2, I give it 3 of them, 3 oxygens. If it's in period 4 down, I give it 4 oxygens. Now, the next thing I want you to note is that group 15 is a family, if it'll let me write. Of 2. Group 16 is a family of 2. When I'm talking about a family of 2, I'm talking about the polyatomics. I'm not talking about how many anions of the element there are. I'm specifically talking about the 8s and the ites. And group 17 is a family of 4. We'll come back to group 17 here in a minute. Right now, I'm going to blow up the family of 2s. See if I can do this where it works. And I want you to tell me the difference between the 8 and the ite.
And everyone except period 2, the 8 has 4 subscript and the ite has a 3 subscript.
Okay. What else can you say about all of them? Including period 2. Well, for nitrogen. The ite has 1 less oxygen. What that means, folks, is I don't need to memorize ite. If I know 8 and I know the rule that ites have 1 less oxygen, I don't need to memorize the ite. Just need to know that I need to know my 8s. So let me just summarize some of the key points to this at this stage. Number 1, for period 3 down, the charge on the polyatomic is the same as the charge on the elemental anion. Number 2, for period 2 8, they all have 3 oxygens. For period 3 down ATEs, they all have 4 oxygens. And lastly, group 15 and group 16 are known as families of 2, which means to go from the 8 to the 8, you drop an oxygen. If you know those 3 rules, your memory work just became a little bit less difficult. By knowing those 3 rules, I know twelve polyatomic ions with only knowing 3 rules. So 3 rules is a lot easier to memorize than 12 polyatomic ions. Now, to help you memorize your charges on period 2, what do you notice about the 8 charges on period 2? It decreases by 1. So in other words, if I know borate's charge, which has 3 oxygens and a -3, then carbonate, because it decreases by 1, means it's got the -2. And nitrate, because it decreases by 1, it has a -1. These are some things that will help you in memorizing your rule or your polyatomics. Now, before I move on to group 17, the other thing I wanted you to note is look at phosphate compared to arsenate. Look at sulfate compared to selenate. As you go down a group, the only difference is the first element. What that means is if you know phosphate, folks, you know arsenate. If you know sulfate, you know selenate, and you know tellurate, because they're identical. In other words, all I really need to do is memorize phosphate and sulfate. And everything else is identical that's below them. Okay, so now let's go over to this family of 4. Some of the things that we've already stated hold true, in that they have the same charge as their elemental anion. So since chloride's a -1, so is every polyatomic ion of chlorine. Since bromine's a -1, so is every polyatomic ion of bromine. Now, but this is a family of 4. Because it is a family of 4, you will notice we have 2 that end in 8 and two that end in "ite." But you can't have two polyatomics that end the same, that have the exact same name. So we add prefixes to the largest and the smallest. The largest gets the prefix of "per," and the smallest gets the prefix of "hypo." So in our family of four, we have 8, 8, ite, ite. But we have "per" for the prefix on the 4 and "hypo" for the prefix on the 1. Now you'll notice, oops, I drew the line for "per" a little bit too low. Now you'll notice though, just like with group 15 and group 16, to go down the family, all you're doing is removing an oxygen. So to go from perchlorate to chlorate, you remove an oxygen. To go from chlorate to chlorite, you remove an oxygen. To go from chlorite to hypochlorite, you remove an oxygen. So that concept still stays the same. Now, take a moment, look at chlorine compared to bromine compared to, well, you can't see all of iodine, but look at chlorine compared to bromine. What you'll notice is that if you can memorize everything about chlorine and its behavior as polyatomics, you know everything about bromine because they behave identically. And the same is true for iodine because iodine behaves identically. So what I just tried to demonstrate helps you hopefully memorize 28 polyatomic ions. And I'm not done yet. I've got a few more things up my sleeve. Oops. Oh well. Now, one more thing I have up my sleeve is this "per" concept. Tell me what you know about, from what you can see here, tell me what you know about "pers." Per-eights, I should, per something eights. What I notice about the per blank 8 is they have 4 oxygens and a -1 charge. per blank 8 has 4 oxygens and a -1 charge. That's very important. Because that is true, period. So for instance, MnO4 minus 4 oxygens, -1 charge, means this is going to be per manganate. Because Mn is manganese. I didn't need to, in other words, I don't need to memorize permanganate. It has the prefix per, so 4 oxygens -1 charge. That's all you need to know is prefix per, it's 4 oxygens -1 charge. I mean, there's one exception to that, and that's peroxide. But the rest of it, per 4 oxygens -1 charge. Now, polyatomic ions, there is another commonality that will help. And that is, let's talk about the addition of hydrogen to a polyatomic ion. So when we add hydrogen to a polyatomic ion, it's in the form of H plus. So we know that this is sulfate. If I add a hydrogen to the sulfate, you can figure out the charge by combining the two charges. So +1 minus 2 is equal to a -1. So this is now going to have a -1 charge. This is hydrogen. So to get to the name, we combine the two. So this is hydrogen sulfate. Another example. This is phosphate. When you add a hydrogen, you get HPO4. The charge is a combination, so +1 minus 3 is equal to a -2 charge. And you combine the name to get hydrogen phosphate. One more example. Let's take PO4 3 minus again. but this time let's add 2 hydrogens to it. So when you add 2 hydrogens, you've got H2PO4. The charge, we're going to combine 2 positive because of the 2 positive and 3 negative. So +2 minus 3 equals a -1. Now, here's the only other issue is we've got to say that we do have 2 hydrogens, and the prefix for 2 is di. So the name would be dihydrogen phosphate. So I'm illustrating this because by understanding how hydrogen would react with a polyatomic, you just eliminated 14 more polyatomics you needed to be able to memorize by learning one basic rule. H comes with an H plus. So when you add an H plus, you combine the charges and that becomes the new charge. And you simply add the name hydrogen or dihydrogen if you add 2 H pluses. We are almost done. I wanted to go back to our huge list, second page. And I want to talk about what some of the things that we just did and how they will help. If I can. It doesn't want to let me have the entire page. So, carbonate. Carbon was in period 2, so that's why it has 3 oxygens, and it's a 2- charge. Nitrate and nitrite. I basically told you, you've got to know nitrate is 3 oxygens and a -1 charge. And this is a family of 2, so that tells you what nitrite had to be. Phosphate is, phosphorus is in period 3, that's why it has 4 oxygens, and it has the same charge as phosphide, which is the element. So that gave you phosphate, and knowing the rule that phosphate to phosphite is the loss of an oxygen, that lets you know phosphite. The rule about hydrogens let you know hydrogen phosphate, dihydrogen phosphate, hydrogen phosphite, and dihydrogen phosphate. The same thing is true for arsenate because it's in the same period. Sulfate and sulfite is the same thing. So you can see, I've tried to give you some rules to help you memorize. Because if you simply try to memorize this table and this table, you'll probably drive yourself crazy. So that is where I wanted to quit today. What we're going to be doing tomorrow is we are going to be talking about ionic compounds. We're going to start naming ionic compounds using the knowledge that we gained today. Any questions? Otherwise, you are free to go, and I will see you on Zoom tomorrow.